Welcome to Lesson 4.3, Configuring Training Parameters. Overview. Training parameters can make or break your fine-tuning results. Too high learning rate? Model diverges. Too small batch size? Training takes forever. In this lesson, you'll learn to configure training parameters optimally for your Tesla P40 GPUs. Duration: 45 minutes. Difficulty: intermediate. Learning objectives. By the end of this lesson, you will understand key training hyperparameters, choose optimal learning rates, configure batch sizes for Tesla P40, set up gradient accumulation, configure warm-up and learning rate scheduling, enable memory-efficient training on Windows, set up logging and checkpointing. Key training parameters. 1. Learning rate. How big each update step is. 2. Batch size. How many examples per update? 3. Epochs. How many times to see full dataset? 4. Warm-up. Gradual learning rate increase at start. 5. Scheduler. Learning rate changes during training. Learning rate. Learning rate equals step size for updating model weights. Too high. Model diverges. Loss goes to infinity. Too low. Training too slow. Might get stuck. Just right. Steady loss decrease. This code snippet is essential for verifying your environment setup before loading models with Unsloth. First, it imports the necessary libraries, specifically Fast Language Model from Unsloth and PyTorch. The next 3 print statements provide crucial information about your PyTorch installation. The first output confirms the version of PyTorch you're using, which is important for compatibility with Unsloth. The second line checks if CUDA is available, indicating whether you can leverage GPU acceleration for faster processing. Finally, the third statement retrieves the name of your CUDA device, which lets you know the specific GPU being utilized. Seeing CUDA available, true, and the name of your GPU, like Tesla P40, confirms that your environment is set up correctly for efficient model training and inference. This output shows the training progress of your model over 3 epochs. Each line under step represents the training loss, learning rate, and processing speed for that specific step. Monitoring the loss is crucial, as it indicates how well the model is learning. Ideally, you want to see this number decrease over time. The learning rate is also displayed, which adjusts how much to change the model in response to the estimated error each time the model weights are updated. As training progresses, you might notice it decreasing, which helps fine-tune the model's performance. At the end of the training, you'll see the evaluation results, including the final loss and the time taken for training. The final loss value is particularly important, as it tells you how well your model is performing on the training dataset. The output confirms that your model has completed training successfully, and you can now move on to evaluating its performance. This Python code defines a function to calculate the total size of files in a specified directory, which is crucial for managing your fine-tuned model's storage. The function getDirSize traverses through the directory, checking each entry. If it encounters a file, it adds its size to the total and prints the size of that file in megabytes, which helps you keep track of individual file sizes. If it finds a subdirectory, it calls itself recursively to include those files as well. At the end, the total size of all files in the output dir is printed, giving you a clear overview of the storage requirements for your fine-tuned model. In the expected output, you'll see the sizes of each file listed, followed by the total size, confirming that your model is relatively small, which is a good sign for deployment and sharing.
Good evaluation doesn't happen with one example. It happens across a deliberately varied set of cases.
Each test case here is a dictionary with 3 fields, a human-readable name so you know what you're testing, an input sentence the model has never seen, and a list of fields you expect to find in the output.
Notice the variety. One case is a clean, simple sentence. Another is complex with multiple attributes. Another has ambiguous or incomplete information. That spread matters. A model that aces the easy cases but chokes on edge cases isn't production ready.
These test cases are your truth table. They tell you exactly where the model is solid and where it needs work.
Testing function.
Rules. Effective batch size 832 is good for most tasks. Larger batch equals more stable, but risk of overfitting on small datasets. Smaller batch equal more noise often generalizes better.
The save pre-trained murdered method handles the merge and save in one step. It mathematically combines your LoRa adapter weights into the base model's weight matrices, the same operation as manually multiplying out the low-rank decomposition, and writes the result as a standard model checkpoint. The save method merged one 16-bit argument tells Unsloth to store those weights in 16-bit floating point, which preserves full training precision while cutting the file size roughly in half compared to 32-bit. The resulting directory will contain a complete standalone model of approximately 6 to 7 gigabytes. Anyone with this directory can load the model directly, no knowledge of LoRa required. The 4-bit merge save follows the same pattern, but the quantization happens during the merge. Unsloth applies 4-bit quantization to the merged weights before writing them to disk, which brings the output down to roughly 2 to 3 gigabytes, less than half the size of the 16-bit version. The quality trade-off is minimal for most tasks. 4-bit quantization with modern methods like NF4 retains the vast majority of model capability. This format is the sweet spot for deployment, small enough to move around easily, fast enough to load quickly, and accurate enough for production use. The output directory name models my murdered models 4-bit makes it clear which format you're working with, a naming discipline that pays off when you have multiple saved versions.
This is a representative base model response to a structured extraction prompt. Notice it's not returning clean JSON, it's narrating the extraction process in natural language, identifying name, age, profession, and workplace as pros.
That's the base model doing what it was originally trained to do, generate helpful text. It hasn't learned your specific output contract. The information is technically correct, but it's in the wrong shape for any downstream system expecting JSON.
This is exactly the problem fine-tuning is meant to solve.
Here's the complete picture of your saving options side by side. LoRa adapters, 85 megabytes, full quality, the right choice for development and sharing. Merged 4-bit, 2 to 3 gigabytes, very good quality, the right choice for deployment. Merged 16-bit, 6 to 7 gigabytes, full quality, the right choice when you need to continue training later. Merged 32-bit, 12 to 14 gigabytes, full quality, for situations where you need maximum numerical precision. GGUF Q4 Kankarske M, 2 to 3 gigabytes, very good quality, the right choice for llama.cpp and or llama. Match the format to the use case and you'll never waste storage or compromise quality unnecessarily.
Analyzing training metrics.
Hugging Face Hub is the standard distribution platform for language models. Uploading your model there gives you free hosting, built-in version control through GitLFS, and a URL that anyone can use to load your model directly from Python. It also makes your work discoverable. Other practitioners can find it, build on it, and give you feedback. For your own workflow, it means your model is accessible from any machine without copying files around manually.
In this code snippet, we're setting up key training parameters for our model fine-tuning process. The variable num_train_epochs is defined as 3, meaning the model will go through the entire dataset 3 times. This is essential for allowing the model to learn from the data effectively. Next, we calculate the total training steps based on the dataset size and batch size. For instance, with 120 examples and a batch size of 4, we determine that we will have approximately 90 steps in total. This calculation ensures that we know how many iterations the model will perform during training. Finally, we set warm-up steps to 10, which is about 11% of our total steps. This warm-up phase is crucial as it helps stabilize the training process by gradually increasing the learning rate, preventing potential issues that can arise from starting too aggressively. For 100-300 total steps, use warm-up steps 10.
Uploading is symmetric with loading. The same push-to-hub method works on both the model and the tokenizer. The repository path follows the format your US GameDate SmartLo name. Replace your US GameDate with your actual Hugging Face US name and choose a model name that clearly identifies what this model does. The token parameter authenticates the upload. If you've already run Hugging Face CLI login, you can omit it and the cached credentials will be used automatically. Crucially, you need to push both the model and the tokenizer. Anyone who downloads your model needs the tokenizer to actually use it. Pushing only the model weights is one of the most common mistakes people make when sharing for the first time. This approach combines the merge and the upload into a clean two-step sequence. First, save pre-trained merged writes the merged 16-bit model to a local directory. This gives you a local copy as a backup, which is good practice before any network operation. Then the HF API class handles the upload. The upload footer method takes your local directory, your repository ID, and your token and streams everything up to the hub. The repo type model argument tells the hub this is a model repository rather than a dataset or space. Once the upload completes, your merged model is publicly accessible at the repository URL, and anyone can load it directly using from pre-trained with just the repo ID. A model card is the readme.md file that lives at the root of your repository. It serves two purposes. It's the human readable documentation that appears on your model's hub page, and it contains machine readable YAML metadata in the front matter that the hub uses to categorize and surface your model. The language field tells the hub your model works with English. The library name field flags it as an unsloth model. Tags like Llama 3.2 and text generation make it discoverable in search. The body of the card should cover the base model, the fine-tuning method, what data you trained on, what the model is good at, and what its limitations are. This transparency is what makes your model genuinely useful to others rather than just technically accessible.
What gets logged? Training loss, learning rate, gradient norm, steps per second.
The training details section of your model card is where you record the specifics of how the model was trained. A LoRa rank of 16, a learning rate of 2E4, a batch size of 4 with gradient accumulation giving an effective batch size of 8. These numbers matter because they let someone reproduce your results or understand why the model behaves the way it does. Recording the final training loss of 0.65 and validation loss of 0.72 gives readers a sense of convergence, noting known limitations, like degraded performance on longer text, is equally important. A model card that's honest about weaknesses is far more valuable than one that only advertises strengths. Including a BibTeX citation block in your model card is a small gesture that makes a real difference for the research community. If someone uses your model in a paper or project, this gives them a clean way to credit your work. Fill in your actual name, the model title, the year, and the hub URL. It takes 30 seconds and signals that you're treating your model as a genuine contribution rather than a throwaway experiment.
The score output function gives you a numeric handle on what you're seeing qualitatively. For each expected field in a test case, it checks whether that field name appears anywhere in the model's output, case insensitively.
It counts the matches and divides by the total number of expected fields to produce a percentage. The loop then prints that percentage for every test case.
This isn't a perfect metric. A field name appearing in the output doesn't guarantee it has the right value, but it's a fast, practical signal for whether the model is producing the right structure.
Use it to triage, then read the actual outputs for the cases that score low.
Loading your saved model. Loading from a local path is exactly the same API as the original model download. That's intentional. Fast language model from pre-trained points to models my first LoRa, and Unsloth knows from the presence of adapter config.json that this is a LoRa checkpoint rather than a full model. It loads the base model from your local cache, no internet required, and applies your adapters on top. The max IX length of 2048 should match what you used during training. The load in 4-bit to car flag keeps memory usage within your GPU's limits. After the 4 inference call, the model is fully optimized and ready to generate. The whole process takes a few seconds once the base model is cached. Loading from the hub is a single line change. Replace the local path with your repository ID. Everything else, the max SXO length, the load in 4-bit flag, the 4 inference call stays identical. The first time you run this on a new machine, Unsloth downloads your adapter weights from the hub and caches them locally. That's roughly 85 megabytes for a typical LoRa checkpoint, which completes in under a minute on a reasonable connection. Every subsequent run skips the download entirely and loads from cache. This makes hub-hosted models genuinely portable. The same 2 lines of code work on your workstation, a cloud VM, or a colleague's machine. File organization best practices. A clean directory structure saves you from confusion as your project grows. Keep all model artifacts under a top-level models folder with clearly named subdirectories for each saved variant, my first LoRa for adapters, my mirrored model _4-bit for the 4-bit merge, and so on. Your training outputs and checkpoints live under outputs organized by run. Datasets go in their own folder separate from model weights. This separation matters when you're debugging. If something goes wrong with a checkpoint, you know exactly where to look without hunting through a flat directory of mixed files. It also makes backup straightforward. You can zip the models folder independently of the training outputs.
This is the ideal output. A bare JSON object, no preamble, no trailing explanation. Just Dane name John, age 45. Every character is load-bearing.
This is what your training data should have taught the model to produce, and seeing it here confirms the format contract was learned.
When you're doing qualitative review, this is the bar. Anything with extra text around the JSON is a partial failure, even if the score function gave it full marks.
Version management. Version your model directories the same way you'd version code. The naming pattern here makes the history immediately readable. Project 1 v1 LoRa is the initial training run. Project 1 v2 LoRa adds more data. Project 1 v3 LoRa. The Project 1 final LoRa directory is the version that passed evaluation and is ready for production. The Project 1 final _4-bit directory is that same final model, merged and quantized for deployment. This structure means you can always trace back to any training iteration, compare outputs between versions, and roll back if a new version underperforms. Never overwrite a previous version. Disk space is cheap compared to the time it took to train. Build version information directly into your directory names. Include the project name so you know what task the model was trained for. Include a version number so you can distinguish iterations. Include the format, LoRa 4-bit GGUF, so you know immediately what you're working with without opening the directory. A name like customer support.v3 LoRa tells you everything you need to know at a glance. Deployment considerations. For local development and experimentation, LoRa adapters are the right default. The file size is minimal, loading is fast, and you can maintain a collection of different adapters, each trained for a different task, and swap between them against the same cached base model. This flexibility is one of LoRa's core advantages. One base model, many specialized behaviors. Before calling this training run done, verify 4 things. First, training completed without a Python exception. An error mid-run means your saved checkpoint may be incomplete. Second, your final training loss is below 1.5 and the validation loss isn't dramatically higher. That gap is your overfitting indicator. Third, your output directory contains checkpoint folders and the final model weights. Open the folder and confirm the files are there. Fourth, your training logs are saved for reference. If all four check out, you're ready for lesson 4.5, loading this model, running real queries against it, and measuring how much it actually improved. The model is loaded, quantized, and fitted with LoRa adapters. The foundation is solid. The next piece of the puzzle is the data, specifically how to format and prepare your training examples so the model learns exactly what you want it to learn. That's lesson 4.2, preparing your training data. Loading the merge 4-bit model for a production context follows the identical pattern. From pre-trained pointed at your merge model directory, max, ax, link set appropriately, and for inference call to prepare it for serving. The key difference from the adapter workflow is that there's no base model involved here. Everything is in one directory. This makes it straightforward to containerize. Copy the model directory into your Docker image or mount it as a volume. Load it at startup, and you have a self-contained inference server ready to sit behind FastAPI or Flask. Exporting to gguf format opens your model to the entire llama.cpp ecosystem. The save pretrained.gguf call handles the conversion. It merges your adapters, applies the Q4-KM quantization, and writes the result as a single .gg. The Q4-KM quantization method is the community standard for a reason. It achieves excellent compression with minimal perplexity increase compared to full precision. The resulting file is roughly 2 to 3 gigabytes and can be loaded directly by Ollama, llama.cpp, and LM Studio with no Python environment required. This is how you get your model running on hardware that has no GPU at all, or on machines where you don't want a Python stack installed. Running your gguf model with llama.cpp is a direct command line call. The isabio model flag points to the .gguf file in your output directory. Make sure the file name matches exactly what was generated by the save step. The prompt flag passes your input text directly to the model. When you run this, you'll see the model's response printed to the terminal. This is your end-to-end validation. If the output is coherent and relevant to the prompt, your fine-tuning, export, and gguf conversion all work correctly. No Python, no Jupyter, no GPU required, just the model file and llama.cpp. Complete saving notebook. Save this as notebook/03 first training/05 save model.ipnb. Keeping it in the same folder as your training notebook makes the workflow easy to follow in sequence.
Work through this checklist before you declare your model ready. On the technical setup side, the model loads without errors, inference mode is active, and the test function returns output without exceptions.
On the quantitative side, training loss is below 1.5, validation loss is below 2.0, and validation loss is not more than 0.5 above training loss. The loss curves show a downward trend without divergence.
On the qualitative side, outputs consistently follow the expected format. The model handles your full test suite accurately, and it outperforms the base model on the comparison prompts without introducing hallucinations. If the checklist passes, save and deploy.
If it doesn't, the retraining signals from the previous section tell you exactly where to focus.
Key takeaways.
Work through this checklist before moving on. On the file side, confirm that adapter model safe tensors and the tokenizer files are present in your models directory, and that your readme.mb documents the training hyperparameters and intended use. On the verification side, reload the model from disk using a fresh Python session, not from a variable that's already in memory, and confirm it generates output. Check the file sizes against the expected ranges. On the documentation side, verify that your model card covers what the model does, how it was trained, and what its limitations are. A model that's saved but not documented is only half done. Key takeaways. Here's what to carry forward. LoRa adapters are your default, small, fast, and easy to share. Merged 4-bit is your deployment format, single file, fast loading, minimal quality loss. GGUF is your format for llama.cpp and Ollama. Hugging Face Hub gives you free hosting, version control, and a shareable URL. A model card isn't optional. It's what makes your model usable by anyone other than you, and backup regularly. Training runs are expensive in time and compute. A backup takes 30 seconds. Module 4 complete. That's Module 4 finished. You've covered the entire fine-tuning lifecycle from start to finish, loading a model with Unsloth, preparing and formatting your training data, configuring the training parameters, running the training loop, evaluating the results, and now saving and sharing the output. You have a working fine-tuned model on disk. That's a genuinely significant thing to have built. What's next? Module 5 takes everything you've built and applies it to chat model fine-tuning, a more demanding and more rewarding problem. You'll work with multi-turn conversations, shape the model's personality through system prompts, and apply optimization specific to dialogue tasks. The foundation you've built in Module 4 carries directly into that work. Multi-turn conversations, personality customizations, system prompt engineering. These are the techniques that turn a capable model into a genuinely useful product. Additional resources. 3 resources worth bookmarking as you continue. The Hugging Face Hub documentation covers everything about model repositories, access tokens, and the Hub API. The Model Sharing Guide walks through best practices for model cards and versioning. The GGUF Format Guide explains the quantization options in detail, which is useful when you need to choose between Q4-km, Q5km, and the other variants for a specific deployment target. Congratulations on completing Module 4. Different export formats make very different trade-offs across compatibility, inference speed, and output quality. TensorRT scores extremely well on speed, but requires an NVIDIA GPU and a specific build process. It's purpose-built for production serving on NVIDIA hardware. ONNX prioritizes interoperability. It runs on a wide range of hardware and frameworks, making it a strong choice when you don't control the deployment environment. The GGUF variants Q4U Kaleum, Q5 Kaleum, and others balance all 3 dimensions reasonably well and are the right choice for the llama.cpp ecosystem. HF-safe tensors in both full and adapter configurations offer full quality with broad framework support. The right format depends entirely on where the model runs and what hardware it runs on. There's no universally best answer, only the best answer for your specific deployment target. This table shows the quantization options for a 7 billion parameter GGUF model, and the numbers here tell a clear story. Q2 Chi is the most aggressive compression at 2.7 gigabytes, but the perplexity score of 12.55 reflects significant quality loss. Avoid this unless storage is genuinely critical. Q4 underscore at 4.1 gigabytes is acceptable for most tasks with a perplexity of 6.12. Q4 Chi-M at 4.4 gigabytes is the community standard recommendation, a perplexity of 5.13 with a very manageable. Moving up to Q5 Cals-KM and Q6 Chi gives you further quality improvements at the cost of larger files, with Q6 Chi reaching 6.0 gigabytes and a perplexity of 5.03. Q8 underscore A is near lossless at 7.7 gigabytes and a perplexity of 5.01, essentially indistinguishable from full precision in practice. F16 at 14.5 gigabytes is full 16-bit precision. For most deployment scenarios, Q4 Kaom is where you should start. This decision tree maps out the paths from a saved model to a running deployment. The first branch is local versus cloud. For local deployment, the GGUF format paired with Ollama is the most accessible option. It runs on a laptop or desktop without a Python environment, and Ollama provides a clean REST API on top. For cloud deployment, Hugging Face inference endpoints let you serve your model with a single click from the hub. For higher throughput, a dedicated GPU server running VLLM or TGI gives you significantly better performance under load. If your model isn't ready for any of these paths, if evaluations reveal problems you need to fix, the answer is to iterate, go back to training with better data or adjusted hyperparameters, and run through the save and evaluate cycle again. Deployment is a destination, not a deadline. This chart makes the storage trade-offs concrete with actual numbers. A full 7B FP16 model and a 7B merged BF16 model both land at 14 gigabytes. That's the cost of full precision. A 7B model with LoRa adapters only drops to 30 megabytes. That's not a typo. That's the power of only saving the delta. The 7B GGUF Q4 Kurosuke M sits at 4.4 gigabytes, which is the practical deployment sweet spot. Scale up to 13 billion parameters and the full model costs 26 gigabytes, while the GGUF Q4 Kurosuke M version brings that down to 8.1 gigabytes. The adapter-only approach scales similarly regardless of model size. Your LoRa adapters for a 13B model are still only a fraction of the base model's footprint. This is why adapters are the default recommendation for development and sharing. The LoRa output directory has a deliberate structure. The adapter models. Save tensors file is the core artifact. This is the actual learner delta, the difference between the base model and your fine-tuned version, stored in the save tensors format for fast, safe loading. At 10 to 100 megabytes, it's remarkably compact for what it contains. The adapter configured.json records the LoRa hyperparameters, rank, alpha, dropout, and which weight matrices the adapters were applied to. Without this file, the adapter weights are uninterpretable. The config is what tells the loading code how to reconstruct the adapter structure. The base model weights themselves are not stored here. They remain frozen in your local cache. The tokenizer files are technically optional if you're loading from the same environment where you trained, but including them makes your adapter directory fully self-contained and shareable without any additional context. The merge and upload workflow has two distinct phases. Phase 1, merge and unload, combines the base model's frozen weights with your LoRa adapter weights, producing a standard model with no LoRa dependency. The result is saved locally with save pre-trained. Always save locally before uploading, so you have a backup regardless of what happens to the network operation. Phase 2, push to hub streams that saved model to your Hugging Face repository. The two deployment paths from there are GGUF export for the llama.cpp ecosystem or direct hub hosting for Python-based inference. Both paths start from the same merged model, so you only need to run the merge once and can export to multiple formats from the result. Uploading to the hub follows a clear sequence. Create your Hugging Face account at huggingface.co. It's free. Create a repository for your model either through the website or via the CLI. Generate a write permission access token from your account settings and authenticate with Hugging Face CLI login. From there, the upload is two calls. Model.save pre-train to write locally, then push to hub to stream to the repository. If you're uploading a merged model rather than adapters, call merge and unload first to produce the combined weights, then push. The tokenizer gets its own push to hub call. Don't skip this step. Finally, add a model card with the language, license, and base model fields filled in. The hub uses those fields to categorize your model correctly in search results. 3 different loading scenarios, 3 slightly different code patterns. For LoRa only loading, the most common case during development You load the base model and apply the adapter in one call using fast language model from pre-trained. This is ideal for continuing training or running quick inference experiments. For a merged model, the loading call is identical in structure but points to the merged directory instead of an adapter directory. This is the pattern for production serving or GGUF export, since the merged model has no LoRa dependency. For GGUF local inference with Llama just PP, you're outside the Python ecosystem entirely. The model file path and the number of GPU layers are the key parameters, and the Llama just PP binary handles everything else. Match the loading pattern to the saved format, and the model will load correctly every time. A well-organized experiment directory makes the difference between a project you can navigate 6 months later and one you have to reconstruct from scratch. The structure shown here keeps everything under a single experiment root named after the task. Checkpoints live in a dedicated subdirectory named by step number, checkpoint Tunch 200, checkpoint 400, so you can resume from any point in training. The final LoRa directory holds the adapter files that passed evaluation, the adapter config, the weights, and the tokenizer. The merge directory holds the production-ready merged model alongside its configuration files. Training arguments and evaluation results are saved as JSON files alongside the model, not in a separate location. The readme.mb ties everything together. This structure is self-documenting. Anyone who opens the experiment folder can understand what's there without asking you. Consistent model naming is a discipline that pays off immediately when you have more than 2 or 3 saved versions. The convention shown here encodes 4 pieces of information directly in the directory name. The base model abbreviated to something like Llama33B, the task domain like customer support, the dataset version as D3, and the training version as V2. Combined, that gives you Llama33B customer support D3 V2, a name that tells you exactly what base model was used, what the model was trained to do, which dataset iteration it was trained on, and which training run produced it. The corresponding hub repository follows the same convention. With this system, you never need to open a directory to figure out what's inside it.